Right, I think we're ready to get started. And like many people in this room, I was present also at Yakir's 80th birthday conference. And I thought I'd dig out the photograph I used then and wish him a happy birthday once again. I did notice, however, having looked again at this picture, that he actually had the number 80 there in the diagram he was showing. And so we must expect to be back with the arrow a little higher in 10 years. And maybe 160 is a bit optimistic, but we shall see. Now, talking of anniversaries, as it's been mentioned, quantum mechanics is about 100 years old. And there's a perception in the community, and I'm sure people in this room, many people in this room would share it, that there's some unfinished business, that there is something still unsatisfactory about quantum mechanics as formulated, and it either needs augmenting or adapting or embedding in something else. And so I want to talk about open questions at the quantum frontier to see where these ideas might be settled in the future. And I've chosen to divide up the possibilities in this simple way that there are three positions. One is that there are no frontiers, that quantum mechanics applies to everything. Everything is quantum. I think I heard Bill use exactly those words about half an hour ago, and that is a popular position in some quarters. Then the second position is that we have the quantum world and the classical world, but we're uncertain about how to form a bridge between them, and Bill mentioned Niels Bohr sort of confused things a bit, but the truth is that the bridge between the quantum and the classical worlds has never been satisfactorily implemented. So unless you think everything is quantum, then there's room for new physics in that bridging theory. And the third position is that quantum mechanics is just a work in progress. It will one day become embedded in some sort of post-quantum mechanics, something that would reduce to quantum mechanics in some limit. And so that's another way in which the business is unfinished. And this is just expressing the same ideas. Either everything is quantum and you're really forced into an Everettian viewpoint, or that quantum mechanics is good as far as it goes, but it has a restricted domain of applicability. And the third position is that we should treat quantum mechanics as really like an effective theory, like Fermi theory of weak interactions. It's an effective theory, very effective. In fact, it's the most effective theory that we know in the implementation sense, but perhaps it is only an effective theory, that there is a deeper underlying theory that will reduce to it in most circumstances, but for which there will be circumstances that it will differ, and then we could test that idea. The basic problem, as I see it, is that quantum mechanics, as it comes to us over the last 100 years, really has two rules that you must apply. We have the unitary evolution when nobody's looking, and then you have the notorious wave function collapse, or the projection onto an eigenstate, and the use of the Born rule when a measurement is made. And the conjunction of these two things has always made physicists feel uneasy. So some sort of post-quantum mechanics would regard the unitary evolution and the projection with the Born rule as limits somehow, and that one hopes that we would have a method of interpolating between those. And of course, weak measurement theory does, in a sense, interpolate between them. It provides a window, at least, into what a theory that would encompass those two rules there as an effective theory, what it might look like. And of course, it might be even weirder than quantum mechanics. It might be something that is very strange conceptually, as different from quantum mechanics as quantum mechanics is from classical mechanics. So, so much for the possibilities, but where do we look for clues to what some post-quantum mechanics might be? Well, there are really three great frontiers. There's the very large, the very small, and the very complex. And what I've done, and this is going to just be a quick survey, I've put together ideas, questions that I think are not just open questions for me, but for a large section of the community, as a way of just getting people thinking about where we might look for new tests of quantum mechanics. So let's take the very large first of all. You can't get much larger than the universe, and so there is a subject called quantum cosmology. When I was a student, it didn't really exist, though Wheeler had blazed the trail back in the 1950s, 50s and 60s, along with Bryce DeWitt, that we might be able to apply quantum mechanics to the universe as a whole. A fantastic extrapolation, 80 orders of magnitude in mass. Can we take seriously the idea that quantum mechanics would apply to the whole universe? Well, if books are anything to go by, clearly we do have to take it seriously. But it does mean that we're going to have to consider something like the quantum state of the universe or the wave function of the universe. And that indeed was a notion that Wheeler and DeWitt introduced a long time ago with the famous Wheeler-DeWitt equation, which doesn't tell you very much. It just says that, that there'll be some sort of operator and some sort of state that would describe the universe, but actually making sense of that is very difficult. What does it mean? What does the wave function of the universe actually mean in the sense of what can be measured? So am I saying that quantum mechanics cannot be applied to the universe as a whole? Well, I wouldn't go that far because I think we have direct evidence that, that the quantum mechanics did apply to the universe at its origin, that the universe was born in a quantum event. And the evidence for that comes from this famous picture, the Planck satellite CMB data. Remember, the cosmic background radiation is the fading afterglow of the Big Bang, and those little temperature variations reflect density variations that were embedded in the universe at the end of inflation, is the interpretation most cosmologists put on it. There was an inflationary era, came to an end about 10 to the minus 32 seconds after the origin of the universe, and that those represent quantum fluctuations writ large and frozen in the sky. And it's an interesting thought that occurred to me as I was putting this talk together, that if you take the largest scale of density fluctuations, incidentally without which we would not be here, because those are the seeds of the large-scale structure of the universe, which became galaxies and then stars and planets and people, that it depends upon the 1 part in 10 to the 5 density variation, delta rho over rho, at the end of this is at the time of decoupling, this picture. So it's an interesting question to ask, well, if you do regard that as evidence of quantum mechanics in the universe, are these really quantum fluctuations? Then you take the largest scale of size for those fluctuations and ask, well, what was the mass at the time, at the end of inflation? And of course, the only length scale that matters here is the gut length scale. That's the inflaton field that's driving this. You put in the gut mass is 10 to the minus 8 grams. And Bill was mentioning the 40 kilogram, and I fully agree with that, but he was also mentioning people trying to create Schrodinger cat states in the lab and look for superpositions and so on. And a paper published just in April has a limit of 3 by 10 to the minus 9 grams, which is, awfully close to what we get from cosmology. So you make of that what you will. I think probably those variations are the classicalization of quantum fluctuations. But does that mean that the universe continues to be quantum, or is there some scale or some length or some time at which the universe then subsequently behaves classically. And that brings me to the subject of the semi-classical theory that Bill just touched on. And when I was here 10 years ago, I spoke on this topic, and I'm calling it stress tensor wars, around about 1975. What am I talking about? Well, the back reaction problem in a semi-classical theory, Bill alluded to this, we're going to have the Einstein tensor, maybe some higher order terms, coupling to some sort of quantum matter, and that we have to have a classical object on the right-hand side, not an operator. We need a number or field on the right-hand side to go with the field on the left-hand side. What is that thing? What is that quantity? Well, I mentioned that Bryce DeWitt was a trailblazer here. He was a student of Schwinger, and he introduced the notion of the effective action and the Schwinger average. So he argued that what went on the right-hand side of that equation should be the Schwinger average. And if you look, you'll see that the Schwinger average is none other than the weak value of the stress energy momentum tensor. It's the same object, the weak value. And it was very fashionable in the mid-70s to use that quantity in a semi-classical theory. And here are 3 papers. This is by Dowker and Critchley, 1976. This is by Hartle and Hu, 1979. This is by Gibbons and Perry. I don't have the date there. So all these people were using this Schwinger average or weak value as the gravitational source at that time. Now, I belong to a dissenting group. We were dissenting at the time. I think Bill was part of that group, Stephen Fulling and others. And we argued that what goes on the right-hand side should be an expectation value. If it's the quantum vacuum, say, it would be the vacuum expectation value of T mu nu, not the weak value. Now, the two of them are related by the formula you see there. Alpha and beta are the Bogolubov transformations between the in-state and the out-state. And the critical thing is that the divergences in the vacuum stress energy momentum tensor are the same, whether it's in or in out. And so you can subtract the one from the other and get a finite difference. And over the years, I think the community shifted to the position that it is the expectation value, that is the appropriate object to go on the right-hand side. But I drew attention 10 years ago to the fact that, that we could reinstate the Schwinger average with the in-out weak value arrangement if we took seriously the idea of the universe having a final boundary condition or a final constraint as well as an initial one. So let me just say a few words about that. Most people think that the universe started simple and becomes more complex over time. It's almost a truism. But we don't know that that is in fact the case. Is that just a prejudice that human beings bring to discussing grand issues, that somehow it seems like the universe ought to be, ultimately a simple thing. And that's, when you look at the vast literature in quantum cosmology or quantum fields in cosmological models, the assumption is that the initial state should be something very simple, like, say, de Sitter invariant vacuum, or in the case of the Hartle-Hawking no-boundary proposal, it was, again, the universe starts out in a very simple state. And then it just evolves, so there's no post-selection. But if you look back in the history of physics, there are plenty of examples of both pre- and post-selection. The selector at the end of the universe, I did my PhD on the Wheeler-Feynman theory of electrodynamics, in which you have a future condition. The universe is opaque on the future light cone. It's an absorber in the future. Then it was very fashionable at that time to consider that the universe might recontract, collapse to what we would now call a big crunch, and that in the contracting phase, the arrow of time reverses. That's an idea that goes back at least to Tommy Gold, if not into antiquity. And it's been visited and revisited. It's like the eternal return, eternally returns, because among other well-known people who espoused this idea were Wheeler himself, Hugh Price, the philosopher, Stephen Hawking. For a while he was saying, yes, the arrow of time reverses in the recontracting phase. And then he, at a very memorable conference in Spain, and maybe Bill was there too, where he retracted that and called it his greatest mistake. So this idea that there could be this reversal if the universe itself behaves symmetrically is a very beguiling one. Hartle and Gell-Mann went on to develop a theory very similar to that. I first heard about that at the same conference that Hawking retracted. There are other ideas around. Kramer's transactional interpretation, Hossenfelder's super determinism also appeal to these ideas of final, in some sense, final boundary conditions. And not least, Aronoff and Gruss, I don't know if that's the correct pronunciation, special natural final boundary condition. And maybe Yakir can tell us a bit more about that. A discussion of this topic must give mention to this book that's doing the rounds, or at least the author, Thomas Hertog, is doing the rounds, The Origin of Time, because this is an example of what I'm saying, selector in the middle of the universe. Back in 2006, Hawking and Hertog published a paper in which they say, in this framework, which they call top-down cosmology, amplitudes for alternative histories of the universe are calculated with final boundary conditions only. This leads to a top-down approach to cosmology in which the histories of the universe depend on the precise question asked. And so this is a little bit reminiscent of Wheeler's famous diagram showing the observer looking back over the history of the universe, deciding what variables to measure, and culling the selection of branches of the wave function. Let me just re-express this in case people are not familiar with this idea. So Heisenberg's uncertainty principle says that we can specify the state of the universe or the state of a system now, and as we go into the future, the future states are uncertain because of that principle, but it's also true going back into the past. The past histories are uncertain. So there's no unique quantum history connecting the Big Bang to us today. There are many possible histories, but if we make measurements, as in Wheeler's delayed choice measurement, we decide to measure position or momentum or something, then that will remove some of the possible histories leading to the present state of affairs. And that's the spirit in which I think Hartle and Hertog are, Hawking and Hertog are discussing this. It got a big splash back in 2006. Hawking rewrites history backwards. If there is something in this formulation by Hawking and Hertog that connects with weak values and final selection, post-selection, then it would be interesting to explore that. Now, I've got to move on because I want to deal with the very small and very complex. There is, of course, the infamous black hole information paradox. Just very briefly, we used to think anything fell into a black hole, we lost all the information about it apart from its mass, charge, and angular momentum. But then Hawking argued that black holes are not black, but radiate and slowly evaporate away. And if they disappear completely, then what happened to the information that fell into the black hole? Does it come back out again? Hawking's calculation said no, his original calculation. It's thermal radiation and therefore has no correlations, no information content. And A lot of people are unhappy with that because they think if quantum mechanics applies to everything, it's a unitary evolution and there's no information lost. And so this is known as the black hole information paradox. I could talk at great length about it. I'm not going to do that because I'm assuming that Lenny Susskind will pick up that topic in a day or two. Then there's a whole slew of things concerning the nature of dark energy, which is really just the energy of the vacuum, and the energy of the quantum vacuum, and the existence of an event horizon in cosmology. It looks like we're asymptoting to something like a de Sitter universe, and that gives rise to the holographic principle. Again, I'm going to leave that to Lenny because that's very much his field. I do just want to mention in passing, though, that the nature of the thermal nature of de Sitter space, I think, is still somewhat peculiar. I think it is not, although there's a close analogue between black hole entropy, horizon area, and de Sitter entropy, horizon area. When it comes to the nature of the heat, it's really quite different. And let me just very briefly say that if you have a inertial particle detector in de Sitter space, it responds as if it's sitting in a thermal bath with a temperature related to the radius of the de Sitter space. So certainly there is a thermal effect, a finite temperature that you can assign to de Sitter space. But when you look at the stress energy momentum tensor, it doesn't have the property of thermal radiation. It doesn't have the 1, a third, a third, a third form that you would get just in a heat bath in the lab. Instead, it looks like the stress energy momentum tensor looks like 1 minus 1 minus 1 minus 1. It's just a renormalization of the cosmological constant. So it doesn't behave energetically, if you like thermal radiation. Then the other thing is that in the case of the black hole, its entropy, as represented by the horizon area, is more or less all of the information you've lost by throwing the particles in. If you just tot it up, how many particles can you stick into a black hole, and add it up, you get the entropy of a black hole. But what is the entropy beyond the de Sitter horizon? It's sort of infinite. It doesn't seem to have any real meaning. And in the case of the black hole, we're very confident that we can talk about heat radiation and entropy because the black hole evaporates and it gives out perfectly ordinary stuff like, just photons with a thermal spectrum, things that we can understand. Just one last comment. I got interested in quantum Szilard engines. A Szilard engine, remember, is a way of extracting work from heat. Of course, to avoid violating the second law of thermodynamics, this has to be rather tightly constrained. I'm not going to go into it, but you can mine a thermal reservoir for useful work. And this is a well-known idea, and you can now, there are quantum models of the Szilard engine. I wanted to know, can you mine the de Sitter heat? So in the very far future of the universe, all other sources of heat are gone, and the only thing around is this miserable thermal background, which a particle detector detects, but it doesn't seem to sort of be real heat. Can you extract energy from it? Could you run your industry and keep going forever? Well, not forever because of the second law of thermodynamics, but could you at least treat it as heat in that source? And so is there, could we have a Szilard demon in the far future of the universe? Well, this will only work if the demon can be in a place that's colder than the surrounding de Sitter space. Can you create such a region? Can you put a shell in de Sitter space act like a heat shield and shut out that residual de Sitter heat? Well, sure enough, you can, at least in 1 + 1 dimension. This is a paper that I just wrote with a student and a postdoc at ASU. And just to skip to the main result, a particle detector inside this confined region, you find a particular quantum state, and the particle detector gives 0 in that region. One last thing about the far future. is the problem of Boltzmann brains. So there's an open question. Some people get very upset about the possibility of, with an infinite future, there's an infinite amount of time for quantum fluctuations or thermal fluctuations, maybe they're the same, interstellar space, generating sentient beings who have experiences. And then the question is, why are we not Boltzmann brains in the far future? Because there's infinitely more of them than there are of us. I'm not going to go any further into that, except that there's some unfinished business there. Another aspect of the very large is that we can, that Einstein's general theory of relativity and most of the refinements of that don't specify which space-times are physical and which are unphysical. Let me just express that differently. You can take any space-time you want and solve Einstein's equations backwards and get a matter distribution that would lead to it. So you can have any sort of crazy, weird space-time, and you can solve to find a matter distribution that will give you that space-time. And yet we feel very uncomfortable admitting space-times with severely weird effects. And a quick thank you to my colleague Malik Parikh for these slides. So we have the space of all possible solutions of Einstein's equations, and then we've got the space of those we would regard as physically acceptable. And to rule out the physically unacceptable ones, there's a whole lot of energy conditions which are added on to general relativity. So general relativity, or its generalization, is augmented by these energy conditions. Basically they're saying energies can't be negative, or pressure can't be negative in some manner or another. And those energy conditions are critical for proving many of the well-known theorems in general relativity. For example, the null energy condition is used to say that you can't make a traversable wormhole, that a black hole, which it was understood right back in the 1930s, has a sort of throat going through it in one representation, is not traversable. It pinches off before you can fall through. And that is a consequence of the null energy condition. But we know in quantum mechanics that the null energy condition can be violated. It's violated by the Casimir effect. And so that led, many years ago, Kip Thorne to suggest that you could maybe have a traversable wormhole with something like a Casimir arrangement in the throat of the wormhole. But of course the magnitude of the Casimir effect, the laboratory Casimir effect, is pitifully small, and so this doesn't seem a very practical proposition. But it does open up the question about whether in principle you could have a traversable wormhole, and Thorne and his colleagues showed that if you could, it could rapidly, easily be turned into a time machine, so that you'd have the possibility of not only visiting the past, but you'd have closed time-like curves. And that led Stephen Hawking to introduce the so-called chronology protection hypothesis, that something would go wrong and prevent an observer visiting their own past, or that the production of these closed time-like curves. And the thing that most obviously could go wrong is that the quantum vacuum would blow up there, that there would be a divergence in the quantum vacuum because of the way the paths go round and around and around. In other words, that quantum mechanics would come to the rescue of what seems like a very unpalatable or unphysical solution permitted in general relativity. So general relativity permits all these crazy spacetimes, but quantum mechanics would appear to come in and act as a restriction. So does that mean that in some sense quantum mechanics completes gravitational theory, which is otherwise left open? I've mentioned vacuum divergence preventing closed time-like curves. I should also mention a famous paper by Larry Ford. So Bill was mentioning squeeze states of light, when you do that, you can have regions of in the field where the energy density is negative and the energy flux is negative. What happens if you direct that at a maximally charged black hole, a Riesner-Nordstrom black hole? It's well known that if the mass of the black hole is reduced by epsilon, then the horizon disappears and the black hole turns into a naked singularity. And that was Roger Penrose's cosmic censorship hypothesis, that there should be no naked singularities, that singularities are always clothed inside black holes. There's always an event horizon. Well, Larry Ford was going to be directing some blobs of negative energy at a maximally charged black hole, making the horizon go away, and the singularity would then be naked, and that would lead to a breakdown of the causal order of the universe. So what was going on there was quantum mechanics threatening to create a crazy space-time. Well, no, because it turns out if you have these squeezed states, then along comes your blob of negative energy, but right behind it is a blob of positive energy. And so the negative energy goes down, the horizon teeters on the edge of obliteration, but boom, the positive energy comes in and restores it. So Larry called this cosmic flashing. It's just sort of wobbling on the edge of existence, but never quite going away. And the rules of quantum mechanics forbid you from removing that horizon. You can do the same thing with an accelerating mirror, but only when the mirror is accelerating towards the black hole. And then you add up the amount of negative energy from the mirror that is going to go down the black hole, and you find that the mirror goes down the hole before you can do much damage. So it is very, very curious that in all these scenarios where quantum field theory seems to violate the energy conditions, you can't seem to use it to create grossly unphysical spacetimes. Why not? Why does quantum mechanics have an obligation to save general relativity from absurdity? I just want to mention that presumably Roger will talk about the inverse of this, that gravitation completes quantum mechanics by collapsing the wave function. We'll see what he has to say. But this idea that quantum mechanics should somehow rescue gravitational theory from absurdity is an interesting one, because we can imagine a sort of great filter in which you write down all of the things you particularly detest in an unphysical theory. Closed time-like curves I mentioned, generalized second law violating solutions. The generalized second law is the ordinary second law of thermodynamics plus horizon entropy. If something made that sum go down, you might want to rule that out. Naked singularities I mentioned. Naked infinity is a similar thing. It's called global hyperbolicity in general relativity. It means information can come in from infinity that could not be captured in any space-like surface on which you might want to set initial conditions. So you might be running an initial value problem, and the universe is evolving, and stuff can come out of nowhere and change your prediction. So you can make a list of all these things, and that may constrain quantum mechanics. It may be that we can put limits on the things that can occur in quantum field theory or some post-quantum mechanics based on that filter of unpalatable spacetimes or gravitational things. Now, enough of the very large. The very small, because I'm going to run out of time, whole different class of issues here. A lot of them around very new ideas of quantum nanoengines, quantum demonics, that's Szilard demons or Maxwell demons at the quantum level as part of nanotechnology and practical engineering. The idea of information as fuel, and Andrew Briggs and I were involved in a Templeton World Charity Foundation program looking at the power of information in physics right across the board, but my interest is the power in here is in the power of information in quantum systems. And there are a whole lot of papers about practical Maxwell demons. When Maxwell suggested his original idea, it took 100 years before somebody actually made a Maxwell demon in the lab, and now it's something of a cottage industry. Here's a paper I just pulled up recently, implementation of a quantum engine fueled by information by Raymond Laflamme and his colleagues. And so this is an active area of inquiry. But it's a very, very ill-understood and difficult area. This is where there are many open questions, because we're often talking about the quantum statistical mechanics of open few-body systems. Very, very hard theoretically, hard experimentally. The converse of this sort of uncertainty and chaos down at that level is the notion of something else, which is still an open question, the idea of time crystals. So Frank Wilczek suggested that just as ordinary crystals break the translational symmetry of space and replace it by discrete symmetry, maybe something breaks the translational symmetry in time and replaces it by a discrete symmetry or periodicity in time. And he had in mind something that would be a quantum system that would be perfectly periodic and in its ground state. It would not dissipate any energy and would not be driven. And I think it turns out there's a no-go theorem for that, but if you allow the system to be driven, you can create something like this periodic system. But I think there are open questions there as to whether time crystals are significant or just, a little quirk. More very small stuff. Bill was talking about, why quantized gravity. Would anybody take seriously a theory in which gravity is classical, and how will we couple it to quantum mechanics anyway? And these are all weighty questions. There are many, many papers, and this is actually quite a recent one, why quantized gravity, but there are many papers going back over many years making arguments that, that you really have to quantize gravity because it just doesn't fit together with quantum matter in any very obvious way. Well, the definitive test of quantum gravity would be detecting gravitons. If you could actually do that, the question would be settled. And interesting, so Bill was talking about LIGO as a quantum system and detecting the photon shot noise. That's one aspect of what he was talking about. Well, can you detect the graviton shot noise? Is that a possibility? Well, that was a question that Frank Wilczek also asked and worked with a couple of my colleagues, Malik Parikh, I mentioned already, and George Hariard, and produced this paper recently, Signatures of Quantization of Gravity at Gravitational Wave Detectors. So they were looking at the possibility that if gravitational waves were in a coherent quantum state, whether next generation LIGO or something like that might actually be able to detect quantum effects of the gravitational field. Maybe relic gravitons from the Big Bang, who knows? So that's an idea. It's an open question. It's a very nice paper. They produce a nice formula at the end of it. And this is something that, who knows, with a future generation of detectors, even more sensitive, maybe something like LISA, the space-based system, might be able to detect this. Moving on, is there any new microphysics that would be relevant to the completion of quantum mechanics? Well, I suspect that Roger will be talking about that, so I'm going to pass on. There's something else about the very small. I mentioned the black hole information paradox. Part of the problem, well, let me just say, I remember discussing this in a hotel room in Boston in 1978 with Stephen Hawking. And the question was, if the black hole evaporates, does it leave a remnant? Is it going to go literally down to zero? And if so, what will happen to the singularity that everybody believes, or believed then, sits inside the black hole? Will that sort of evaporate as well? Or is it possible that some sort of Planck scale remnant could be left? And the difficulty, as it's seen now, is that can you have such a vast amount of information, vast number of degrees of freedom packed into that remnant? And these are open questions, but many people working in quantum gravity think that the information that is contained in the black hole somehow leaks out in correlations in the Hawking radiation between the sort of early and late times. They're hidden, buried somehow in that radiation. There are many ideas around. I'm not going to summarize them all here. But if it's possible that most of the information gets out, we still have to ask, could there be a Planck scale remnant? And some people think that this is indeed the case, and that there's dark matter might be primordial black holes which have evaporated down to a Planck size. Another open question. I think everybody who works in quantum gravity would feel that the Planck length is a fundamental length, and that something will seriously change in our understanding of gravitation and the nature of space-time down at that level. And I have a collaborator, Phil T., who's interested in the idea of space-time being an emergent property, emerging from some discrete substructure, some sort of network or lattice system. And he kindly put together a couple of slides for me on what we're calling pixelated space-time. And the problem is there are many, many different groups taking many, many different positions on this topic. So I don't have time to go into any of them in any detail. The only one I've been involved in, along with Phil T., is something called doubly special relativity. That's down there, doubly special theories, due to Giovanni Amelino-Camillo. There's another slide which organizes things slightly differently. Things over on the right are discrete space-times from which some sort of continuum emerges in the limit, and those on the left probably assume some sort of underlying continuity, but the space-time that we know and love on the macro scale emerges from some more complicated quantum type system on the micro scale. You see, this is a vast area, a whole industry of people, many of whom don't talk to each other because they work in different blobs or don't even like each other, have very different points of view. These are all open questions. There's one that's always bothered me, and Ted Jacobson is the evangelist of this problem, the so-called problem of trans-Planckian modes. That if you think the Planck length is a fundamental length, that's a length size, that gives you a fundamental frequency, a maximum frequency, the Planck frequency. And many people think, well, we cannot extend our physics beyond the Planck frequency. It ought to act as a sort of cutoff. But the problem is that what is a Planck frequency today was trans-Planckian yesterday when the universe was a bit smaller. And so what does that mean? As the universe expands, if you're going to put a cutoff at the Planck length, or the Planck frequency, then new modes have to be created to fill in the gap. Same is true of any sort of pixelated universe, that as the universe expands, you need more pixels. They've got to come into existence. So that seems like an open question. We don't know how to interpret that. And then in Stephen Hawking's original calculation for black hole radiance, he used a Bogoliubov transformation between the in and the out states, where you integrate over all frequencies to infinity. And if you put in a cutoff at the Planck frequency, you don't get a steady flux of radiation, you just get a little puff. But nevertheless, that was a very idealized initial calculation. Some more messy one might still give you the same result. But again, I asked Ted Jacobson, well, how do you feel about the Hawking calculation? He said, well, that particular calculation is probably not very relevant anymore, but what is still relevant is where does the Unruh vacuum come from? Because Bill's simplified vacuum state for the case of black holes mimics, so we believed at the time, I'm pretty sure it's the case, mimics the quantum state you get if you start out with a Minkowski vacuum and a collapsing body and just let it implode to a black hole. You would end up producing something like the Unruh vacuum. But without the original calculation, with the trans-Planckian modes, where does it come from? What's the explanation? I don't know, maybe Bill can tell us. Now, in the last few minutes I have available, I want to turn to the final frontier, the frontier, the very complex. And this is where we hit a whole slew of stuff having to do with measurements and observations and consciousness and all of these things that people like to argue about. The big problem about quantum mechanics, as I described it earlier, is it doesn't tell us what a measurement is. It just says when a measurement takes place, the wave function collapses, you use the Born rule. But it doesn't tell you what it takes. Indeed, the Heisenberg cut, as it's referred to, can be moved all the way from the atom up to the brain. There seems to be nowhere where quantum mechanics tells us there should be a transition. Is there such a transition? If so, what physics is going to give that to us? We don't know. Except I come back to the point that weak measurements are a sort of window on this, that we can imagine, because they are non-projective measurements, they're not, as it were, collapsing the wave function. So if consciousness has anything to do with wave function collapse or quantum measurement or quantum events, anything whatever to do with that, weak measurements ought to be a good way of giving us a clue as to what's going on. Can you have weak consciousness, weak observations? You can have weak measurements. What about weak observations or weak consciousness? Can you have weak qualia? Might there be, in addition to beings like us that do strong projective measurements, giving us a concrete world with definite values, might there be weaklings who observing the world entirely through weak measurements? And that leads me to ask the question somewhat differently. What is an observer, and can there be observers in Hilbert space? Do observers have to be classical? Do they have to be wave function collapsing entities? And this is thrown into sharp relief recently with the rise of AI and discussion about is ChatGPT-4 conscious and so forth. Well, I'd like to take it a step further and think about quantum AI. So we combine now quantum computing, one great hope for future tech, particularly here in the United States, and AI, the other great hope for future tech. We merge them. We get quantum AI, and that's what Frank Wilczek has long been calling quintelligence. Is that a prospect? Well, if you believe that AIs can be conscious, then surely we have to ask the same of quantum AIs, and that raises the whole question about would a conscious quantum observer see the world differently, and could it tell us more about the deeper nature of reality? And that's a question that I asked long ago of David Deutsch, because I made a BBC half-hour documentary about foundations of quantum mechanics, and in those days there was almost nobody prepared to argue for the Everett interpretation. Now people tend to think, well, this is the party line, but then it was considered very eccentric. But David was an evangelist of Everett, and here we were in those days. You see, we were a bit younger, and the transcript of that appears in the book that came based on the series, The Ghost in the Atom. And I was trying to dig out the actual audio of an exchange that David and I had. I couldn't find it. I've got the text. I can't read all this. I just want to pick it up. He's basically suggesting if we had a quantum AI, as we would call it now, or quintelligence, we could ask it to perform an experiment to tell us whether there are many universes or one. And I'll pick up the conversation partway through. So I say, so we have an atomic system with two possible states, each of which would trigger the brain of this artificial observer to be in either one state or the other. And according to the Everett interpretation, you're saying, David Deutsch is saying, that these two brain states somehow coexist, or at least exist in parallel universes. But we don't let the universes get out of touch with each other. We bring them back to overlap, to interfere with each other, and this poor observer is, as it were, schizophrenic and observing both of these possibilities at once. And apologies for the sexism, we designated this entity to be male. So David Deutsch replies, that's right, in effect, he is feeling himself split into two copies. Of course, we don't have sense organs of this type, so it's hard to say what this would feel like. But when this observer exists, we can ask him. Davies, it sounds most uncomfortable. Deutsch, perhaps it will be, but then presumably he'll be a physicist, so he'll enjoy doing the experiment. Well, there we are. So the idea of quintelligence goes back really a long way to the early 1980s. So I want to ask this, I think we have all, and I think I just got about 5 minutes, we have all agreed that it's unlikely quantum mechanics breaks down at some scale of mass, at least not up to 40 kilograms, and you might as well go almost to infinity then after that, or physical size, the blobs in the sky and so on. But what about at some level of complexity? Is it possible that quantum mechanics is great for sort of simple or linear systems, but as soon as you start to get to something particularly complex like a living organism, like a cat, then maybe it breaks down because of the departure from unitarity because of the complexity of the system. And even if that is not the case, even if we don't find that as you get into more and more complex systems, quantum mechanics breaks down, or there's deviation or adaptation, is it the case that quantum effects still bleed into biology to some extent? And this is the last topic I want to cover. Schrödinger himself considered this back in 1944 in his famous book, What is Life? He was asking, can life be explained by physics? I don't know any physicists who would say no, but of course the issue is not, can it be explained by physics? Can it be explained by known physics? Or does it need new physics? Does life need new physics? And Schrödinger himself was open-minded. He said one must be prepared to find a new kind of physical law prevailing in it. Notice he didn't say a new law, not just, we add to electromagnetism, gravitation, a law, some law governing biology, but a new kind of law, a new concept. If you want to know my thinking about it, you can dig out this copy of Physics Today. Is there new physics lurking inside living matter? I want to jump over the next two slides simply because I'm running out of time. That was a quote by Max Delbruck, and this is a cute little pussy, but never mind. I want to point out that in biology, whether quantum or otherwise, the traditional notion of laws of physics are not a good fit. The idea of of taking some initial condition and some boundary condition and then applying fixed laws and rolling forward. And the reason is that biological systems are generally open systems and they can undergo dramatic changes. And there are rules, certainly, it's not anarchy, but these rules depend on the state of the system. So we led to the notion of state-dependent dynamics, a topic that I could have devoted this entire hour to, but I'm not going to do that. But it was recognized by Darwin himself that this distinction about the planet Earth cycling around the sun according to fixed laws for billions of years, whilst all the time life is evolving and doing new things. It's open. It's exploring state space in a fairly unconstrained manner. And so, but trying to apply any type of physics in the traditional sense to biology on the large scale, not just at the level of individual atoms, it doesn't seem terribly appropriate. So we want to know, does quantum mechanics play a fundamental role in life? As Schrödinger sort of hinted, and a number of his contemporaries thought that quantum mechanics explains matter all the way from the nucleus up to white dwarf stars. Does it explain living matter? Looked like it was that we were stuck with living matter. And most biologists would feel that ball and stick chemistry explains all of biology. But if that's the case, what it means is that at the level of biological systems, they're being treated as classical systems. So has there been a transition, or are the quantum effects simply too small to matter? There are two ways in which quantum mechanics might be relevant to life. One is it could limit the ability of life to do clever things at the molecular level because of quantum uncertainty. That this is, would seem to go against the idea of life trying to do things reliably and to advantage. But on the other hand, it could be a positive effect if there are quantum processes that amplify or enhance the performance, biological performance, then life is likely to have discovered that in 3.5 billion years of evolution. So if there's a quantum edge, even if it's like, say, a 10% improvement in some process, some vital process, then it's very likely that life has discovered that. And that's led to the dawn of a field called quantum biology. Does it really exist? Some people say, well, all biology is quantum because chemistry is a branch of quantum mechanics and life is chemical. But what I mean by quantum biology is non-trivial effects like tunneling and entanglement and superposition and so on. Do those phenomena play a role in biology? And if so, do they play a fundamental role or just an incidental role? And it's clear that here and there they do play a role. You don't have to go very far from Chapman University to find your local expert. Clarice Ayeo runs the quantum biology lab at UCLA. Sometime you might want to invite her to come and give a lecture. I just went to a whole conference in London on quantum biology, and most of the excitement these days surrounds the avian compass. The birds navigate using the Earth's magnetic field, and it looks like they do this by exploiting quantum chemistry where radical ion pairs can be in singlet or triplet states, and the chemical products from those states are sufficiently different that they would lead to different neurotransmitters that the bird could then differentiate between them, and so that in effect means, and in the eyes of the birds are molecules called cryptochromes with a fixed orientation, and photons can create the radical ion pairs, and then the Earth's magnetic field, the direction of the field, will affect the admixture of singlet and triplet, enabling the bird to literally see visually a pattern, a field pattern corresponding to the Earth's magnetic field. And so there's been a lot of attention given to this avian compass, but it turns out that this hypomagnetic, small magnetic field, so it's very important. If you put a bird in an MRI machine, this is all messed up because very strong magnetic fields just saturate the effect, but a weak magnetic field is sort of poised exactly to exploit these quantum effects of quantum chemistry. And there seem to be many other biological effects of hypomagnetic fields, a whole review article here. There's, again, a vast industry of people working on this. So another thing people work on, quantum effects in photosynthesis, the transfer of the energy from the light harvesting molecules to the reaction center where the water is split seems to involve some quantum beats, some quantum coherence. Then there's another set of problems people are looking at about the conductance properties of biological molecules. This is electron conductance or tunneling through quite complex organic molecules. And the work of Gabor Vate in particular, if I just quote that in this paper, we show that practically all biomolecules, from small signaling molecules to proteins, taking part in biochemical electronic processes, belong to a fundamentally new class of conducting material. This is a disordered conductor where the strength of the disorder is tuned exactly to the metal insulator transition point and is consequently in a permanent critical state. So this is quantum criticality being exploited by biology for electron transport purposes. So the question I'm leaving you with then is quantum biology. Are those examples just the tip of a quantum iceberg, that life is fundamentally quantum, as Schrödinger might have once hoped, or are these a few quantum quirks picked up along the evolutionary way? The ultimate problem of quantum mechanics and consciousness I'm going to leave to Roger. I just want to mention, because this is the last slide, that the traditional assumption that there's a connection somehow between consciousness and wave function collapse, it could just be that each of these is the outcome of a deeper theory, and that deeper theory might be integrated information theory. That's a way of quantifying the complexity of a system. If it's true that quantum mechanics breaks down or transitions to something else at a sufficient level of complexity, then one measure of that complexity is integrated information theory, which is a theory which purports to quantify consciousness. If it can also quantify wave function collapse, then we found our correlation between consciousness and wave function collapse. It's not that consciousness causes wave function collapse, it's that they're both an expression of a certain, beyond a certain threshold of complexity as measured by integrated information theory. I should say right away that IIT has been criticized. It's probably not the right prescription, but something like that where we can quantify complexity as a way to attempt to get to grips with consciousness might also apply to quantum mechanics. I'm not the only one to say that. Here is a recent paper by David Chalmers, Kelvin McQueen, applying integrated information to wave function collapse. Final slide, weirder how. Well, Daniele already took my joke. Obviously something completely different. And so at that point, I think I better stop. I think I am exactly on time if it was 1 hour. Right.
Thank you, Paul. Question or two?
Very short one, really very short.
Yeah.
In view of the fact that we are celebrating Yakir's 91st and so on, maybe it should be mentioned that the idea of the remnant, a Planckian remnant, storing the information and whatnot, was suggested by Yakir, by Aaron Kasher and myself, prior, I think, to the distinction and other. And specifically, we suggested that it will be dark matter if you start with the quantum era.
Well, it's very remiss of me not to know that on this occasion in particular, but very remiss of me not to mention that work, because it's an idea that it goes back a long way, as you know, and then it seemed to go out of favor for a long time, but just very recently it's come back into favor. And I think the reason for that is a growing belief among people who really think quantum mechanics applies to everything, that the information can leak out of the black hole, and you could have a remnant without it being, super many degrees of freedom.
Question from Tom.
Thanks for the interesting talks. I have several comments, but I will give only one remark. As I see it, consciousness is totally different thing than intelligence. And consciousness, as I see it, is this internal experience. And thus, it cannot be quantified by any means.
Right, and your position, I think, is fairly conventional, and I don't necessarily say I disagree with it. And certainly, consciousness and intelligence are very different things. It's just all this stuff has been, out there in the blogosphere in the last year or so. I don't take it too seriously.
Yeah, so I cannot also think about QAI with respect to consciousness. Totally different things.
Right. Well, I'll defer to Frank Wilczek on that one. I'm open-minded, but if it turns out that we can simulate consciousness by some architecture that maybe IIT is it probably isn't it, but something like that would give us a plausible measure of what it would take for consciousness, then we could imagine designing a quantum computer that would have the appropriate circuitry with these appropriate feedback loops to implement it. So this is not totally absurd, but we're a long way from it yet. Are we allowed any more questions, or should I'm waiting to hear David's result, because I was going to say what we need is a philosopher to untangle all this, and I'm looking at you, David. And so perhaps some of these questions will be answered. Some of these open questions will be closed by the time we have cocktails.
So I suggest we continue this in the cocktails.
All right, thank you.